Emiche, how are you?
Morning, sir. I'm good, and you?
Hi, Emiche, can you hear me?
Yes, sir. I can hear you.
Can you
Hello,
please
sir.
confirm if you can hear me? Oh, I had my earphones on. Can you please confirm if you can hear me now?
Yes, sir. I can hear.
Okay, remember what we did last time, right?
Yes.
We're going to continue from what we did last time. We stopped at work energy theorem. And how many minutes am I owing you from that session?
It was 40 minutes.
30 minutes.
Yeah.
Please, I need you to write all the hours down there. For this month, for your second month of tutoring with me, we haven't covered anything yet. Ne? We haven't done any hours. I think so. Ne? I don't know, but please, I'll be happy if you can also confirm that for me. Okay?
Okay, sir.
Okay. So we're going to work on. We'll do work energy theorem.
Okay.
Okay. Okay. Let's do this. Right. So if you have any questions, please do ask me now. And if I'm moving fast, please tell me to stop now.
Yes, sir.
You understand? So now, when we work with the energy theorem, I'm not sure if you still remember the concept of energy theorem, where it says the work done by a net force is equals to what? It's equals to the change in kinetic energy of the object. You still remember this concept?
Yes, sir.
Nice. So, and what is the formula for the work energy theorem? Which formula do we use to
We didn't.
calculate?
We didn't get this, so you just put this thing.
And then the power went off.
This. Yes.
I'm sorry about that time, ne? And how
It's
long did you
okay.
how long did you wait for me?
I waited. I think I waited till the class was finished, and then at some point I just stopped.
I'm sorry, ne?
It's fine, sir.
I'm very sorry. Okay, okay. So now look at this. I'm going
Mm.
to write the formula down. Just give me a second. So the work, we're going to say the work, the net force, the work done by the net force, it equals to the change in what? It's equals to the change in EK. Right, now we need to understand what we mean when we say the change in EK. Remember that the formula that we use to calculate the net force, which formula do we use? Which formula do we use? Remember that. Okay, I'm listening.
What is this saying? I'm confused now. What are you asking?
Okay, like the formula for net, the work done by net force. Remember, it's F net multiplied by the displacement, which is delta x. Now, the formula for change in EK is half mass inside the bracket. We're going to say this is my VF final. Né? So this will be my V final. And remember, this V final should be squared. We're going to minus my V initial squared. Are you happy with that?
Are you writing?
Yes. Can you see my screen?
Because I see your screen, but I don't see the formula that you just wrote now.
You don't see the formula?
No, all I see is work energy theorem or the definition.
Okay, let me quickly fix that now. Okay, I'll definitely fix that. Auntie, what's wrong? Okay. 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 Can you see the screen now?
Oh.
Not yet.
No. Okay, yeah, now I see it.
Okay, all good, ne?
Yeah.
Okay, please tell me if you can see what I'm about to write now. If you can see what I'm about to write, then we're going to continue with the lesson, okay?
Okay, it's fine.
Right, so now, what I'm saying, okay. I'm saying that this is the formula that we're going to use to calculate the work energy theorem. So now we need to put something on inclined, then we'll be working on applying this formula, okay?
Okay.
Right, I'm going to put the incline. Please tell me that you can see my box, my incline. You see my writing?
No.
Come on, Emichi, don't see anything.
No, I'm still waiting. Okay, now it's showing.
You see the box?
Yes, I see the incline in the box. Yeah, now it's completed. Okay, yeah.
Oh, okay, no problem. So let me quickly just fix this now. Okay, I'm just gonna put my incline like this. Okay, there's my incline, and then I'm going to say
maybe it's net. I think maybe it's network because I see it matter. It's taking slow. Like I'm not moving with your pace. It's
Oh,
like
okay.
glitching, and then it does glitches.
Okay, I know what we need to do now.
Okay.
Okay, you'll tell me how it is now, man.
Okay.
I definitely know what we need to do. I'm very sorry about this, né?
Okay, sir.
Okay. I'm trying to fix the issue. Oh, don't worry. We'll improve again.
Yes, sir.
We will improve. Okay. Tell me, can you see now?
Yes, it's
okay. Let's do this now. I'm trying to fix things here. Then I'm just gonna try and write something. Then I need you to tell me if you can see what I'm currently writing. Okay.
okay.
Okay, so we're going to put a box here on inclined. Right, so the box is on inclined. Can you see my writing now?
Yes.
Nice. Okay, so let's say that the distance of the inclined, the distance here, let's say the distance between our slope, we say the distance, let's say, is given as 5 meter. Okay.
Okay.
Okay, so we're just gonna say the distance is given as 5 meter. Please just give me a second. Okay, nice. I think everything is good now, ne?
Yes.
Right. So the distance is given as 5 meter. So this is what we have now. And then let's say the weight of this one is 100 kg, okay?
Okay.
Nice. The weight is 100 kg. So if the weight is 100 kg, and then let's say the box started by, let's say the box was on this point here. This is where the box or the object started, ne?
Okay.
So remember, if I have an object and inclined, the most important thing that we need to do is to identify what the forces that are acting on that object. It's very important that we know which forces are acting on the object. Okay.
Okay.
Right. So now, when it's like this, remember from this box will experience what? The weight, and we're going to call the weight Fg. I think that one is easy. And then if it has the weight of Fg, there's a weight that will be perpendicular to the surface. And that weight, what do we call the weight that is perpendicular to the surface?
Fg perpendicular.
Exactly. It's perpendicular to the surface, and that weight we're going to call it Fg perpendicular. I think this makes sense because now we know that the FG perpendicular is the one that is opposite to 1 is the one that is opposite to the normal force, ne? Right. So if this is my FG perpendicular, there is a force that is parallel. There is a force that is parallel to the surface. What do we call that force? There is a force here that is moving down. What do we call that force? What is called that weight? Let's call it a weight. What is that weight?
FG parallel.
Okay, FG parallel. Okay, so now if you say this is my FG parallel, now can I move the FG parallel and write it here instead? And say this is my FG parallel so that we can form a 90-degree triangle. So can you see the triangle, just the one that I just created now?
Yes, sir.
Okay, thank you very much. The YouTube part, guys, please comment if you can see and if you can hear me correctly. Please, guys, just bring your comments. I'm waiting for you guys. Sorry I'm late, Evelyn, no problem. Okay, so now when I have this, I'm just gonna write some of the information down just to remind you that the FG perpendicular, the formula that we use for FG perpendicular, we said is going to be FG the cos of theta. You understand? FG the cos of theta, and then we have FG parallel, and this is equal to what? This is equal to FG the sine of theta. Okay, we already know where these formulas are coming from, and let's say that the angle here is given as 30 degrees. Né?
Yes.
So we have this is not let's say the mass. If we work with a bigger mass, maybe we might have a problem, but let's just say 10 kg instead. Né? So the mass is 10 kg, and let's say they want us to they say this is pulled up a slope. So this object is going up. We can see that it starts at point A, then it moved to point B. Okay. Okay, so it starts at point A and it moves to point B. So now look at this. We have the force applied. We're going to have the force applied. So now I'm going to remove that FG parallel because we know where we have FG parallel. I need to move this so that I can have a space to do what? To write my force applied. So I'm going to say this force applied, it's moving up. So the object will move from A to B. And now we have the F applied. The force applied is given as 800 newtons. So the F applied is equal to 800 newtons. Né?
Okay, sir.
You see? So we are saying that the F applied is equals to 800 newtons. Okay, with this information, we're going to say that let's say the friction between the box and the slope is 25 newtons. So let's say we have the frictional force. I'm going to call this Fk. Let's say this is 25 newtons. Remember, it will go down since the object is moving up. Né? That's the frictional force. And then if the box starts from rest, the question says if this box start from rest. Let's say it starts from rest. So if it starts from rest, tell me what will be the velocity?
0.
0. So let us determine, we're going to determine what? We're going to determine the magnitude of the velocity. The magnitude of the velocity. We're going to determine the magnitude of the velocity of the box. The magnitude of the velocity of the box at the top. At the top of the slope. Do you understand the question? Because if you understand the question, everything will be good, ne?
Okay.
Do you understand what is the question saying?
That if the box is not moving right, they're asking us to calculate the magnitude.
No, the box is moving, but they want us to note that it starts from rest.
Okay. At the beginning, the velocity was 0.
Exactly. So it starts from rest. So if it starts from rest, what we're going to do is that the initial velocity is 0, and they want us to do what? They want us to find the velocity of the box at the top of the slope. So what I'm going to do, we're going to use that formula where it says the work done by net force is equal to the change in what? The change in EK. Okay? Then what we're going to do, you just have to be able to know what is your net work done. You need to identify all the forces that are working on the object. I'm going to start now, and I'm going to move slow now. So we're going to start by drawing a free body diagram. That is very important, because the net work done means that we need to identify all the forces that are acting on the object, and those forces should be parallel to the what? To the surface. So I need the force that are parallel to this incline. I need to identify those forces. That is very important. So I'm going to say I have F applied going up. This is my F applied. Then I have my frictional force going down. Then there's this other force that is going down. Which force is that? There's a force. Which one?
FG parallel.
Exactly, the FG parallel. So I'm going to say this is my FG parallel will move down. So let's take up as positive. So if you still remember Newton's law, the reason we started with Newton's law, we wanted to do this so that you can understand how these things work. Right. So now look at this. Now, if I have F net, I need to find the net work done by all these forces. So I'm just going to choose up as positive. So this will be the work done by what? By applied force. We minus the work done by the FG parallel. We minus the work. Okay, let me minus the work done by friction first, because remember the friction is given. Let's say the work done by FK. We're going to minus the work done by the FG parallel. I think so far you understand where is this coming from, ne?
Yes, sir.
Right. Remember, we are still on this formula. We are still on the formula that the net work done by forces is equal to the change in what? The change in EK. So the formula for change in EK is just 1 over 2m. Inside of the bracket we take 1 over 2. So this will be Vf squared. We minus V initial squared. Okay?
Okay.
Are you happy with that?
Yes, sir.
So now you can see that there are some of the things that we need to calculate. There are some of the things that we need to calculate. So remember we talked about the formula last time that we can use to find the net work done by a force. For example, if I want the work done by applied force, I can use the formula and say my force applied multiplied by the displacement. You understand again?
Yes, sir.
So that's the formula I'm going to use. It's the applied force multiplied by the displacement. So I'm just going to substitute this because I don't waste time. We already wasted 15 minutes of this lesson. Ne?
Okay.
So the work done by applied force, we know that is going to be that 800 newtons, the one that was given, which we need to, okay, it's fine. Let me substitute this so that I don't make any mistakes. So I'm going to say this is the work done by applied force multiplied by the displacement minus the work done by kinetic friction is going to be the work done by frictional force, we're going to multiply by the displacement, minus the work done by Fg parallel. Remember what is Fg parallel equals to? Fg parallel is equal to mg the sine of theta. It's equals to mg the sine of theta. I get it? Fg parallel. Remember that Fg parallel is equals to Fg the sine of theta. And what is the weight? We use the mass times the gravitational force. Is this, you understand? Is this making sense now, ne?
Yes, sir.
Right, but remember, even this guy, we still have to multiply this guy by the distance, which is the delta x. Then we need to equate this to 1 over 2m into v f squared minus v initial squared.
Wait, sir.
I'm moving fast, ne?
Yes. I was gonna ask the reason why we times all of it by the delta x. Is it because we said f net times delta x is equal to half mv2 minus vi2?
Please come again. You saying?
Remember, right on top, just before we did this whole thing on top, we wrote that formula that f net times delta x is equal to that EA formula.
Yes.
So the reason why we times all of them by the delta x is because of this formula.
Yes.
Okay.
It's because of f net delta x.
Okay.
This is the formula. So now we just have to do separately for each force.
Okay.
Even last time we did work through this one. I'm not sure if you still remember, but we said the formula for work done, the formula that we can use for work done, it's F times the delta x, and I showed you the other one formula. I think it's best if I put this on the board so that you can remember what we did last time, ne?
Yeah.
We said that last time the work done by a force, if I want to find the work done by applied force, I can use the formula of F applied delta x, or I can use a formula and say F applied is equals to the work done by applied force, it's equals to F delta x times the cos of what? The cos of theta. So each formula is going to be correct. So I prefer using this one when we work with the work energy theorem, not that one. So this is the formula that we use to calculate the work done by applied force on that object.
Okay.
All good, ne? Okay, nice. So if you understand this one, can we now do the substitutions?
Yes, we can.
Okay, so now look at this. I have my applied force, and what is applied force equals to? It was given as 800 newtons, ne?
Yes.
So the applied force was given as 800 newtons. So I'm going to say this is my 800 multiplied by delta x. What is the distance? This should be easy because the distance was given and it was 5. The distance the object traveled is 5 meters. So I'm going to substitute this as 5 minus Fk was given as 25. We need to take the 25 of Fk multiplied by 5. So this will be 25, which is need to be multiplied by 5, minus the mass is 10 into 9.8. The sine of what? The sine of theta. Which angle are we using this time? The angle of what? The angle of inclination. So if you are working with these two angles, we use 30 because this is the angle of inclination.
Okay.
Nice. So now if this is the angle of inclination, this will be the delta x, it's 5. I'm just going to substitute 5. This should be easy, né? 1 over 2, and the mass is 10. And then we are looking for the final velocity. So I'll just leave my vf squared. We minus the initial velocity, and it was given at 0. Why? Because it starts from rest. They said this starts from rest, so the v initial will be 0 meters per second. You understand?
Yes, sir.
So now I need to see if you can isolate vf. Can you please work this thing and tell me what you get as your final velocity?
Okay.
Okay, so now if we check, we look at this. Someone is saying, say what will happen if magnitude doubles. And okay, even if the magnitude, I'm not sure if you are referring to the applied force or what, but still we can work it out. There's nothing wrong with the magnitude being doubled. And then edits, rain edits. I hope I answered your question. They say, so can we choose direction, or we just let our guide us? No, always choose direction. You know, the best thing to do, treat work energy theorem the same way you do Newton's law. Ne? The same way, you see, guys, it's very important that you start answering your question by drawing a free body diagram. So it's very important that you start by drawing a free body diagram. Ne? Very, very important. Please consider that. Ne? Very important. And what is your VF squared equals to if you isolate the VF? What did you get?
I'm not done yet, sir.
You're still working on it?
Yes.
Okay, no problem.
I'm sorry, sir.
I know that this time this is just S5 VF squared. It's equals to, I just need your help to punch this other side on your calculator and tell me what you get. So
How much? What was your calculation on the other side, sir?
let me, when I put this left hand side, I get 7, not 7, I get 1,452. Then I need to isolate this, isolate that by dividing both sides by 5. So if I divide both sides by 5, I get my VF squared as 726.
Yeah.
Then what is your answer when you square this? What is your V final equals
to? Should I give in decimals?
Yes.
Okay, so it's 26,94
meters per second. So where is this going? You can say upwards, ne?
Okay.
Are you happy with this problem? Any questions?
No.
All good, ne?
Yeah.
This was easy, ne?
Yeah, in a way.
Okay, now you know what let's do this, ne? Let's just do this. Let's say that I have an object like this, ne? The very same object. This is my horizontal surface. So now this object is going to travel, let's say the object travels from an inclined first, né? Or maybe let's say we put it here and say this is my 10 kg, then it's going to travel all the way up the inclined, okay?
Okay.
Right, it's going to travel all the way to this point here. That is the object. So now this is the same 10 kg block is traveling on a frictional surface. You understand? A frictionless surface. So what we are trying to say is that we don't have a friction on the ground, something like that. So the box encounter a rough slope. So now this part here, listen, because I can't just write the whole statement. I'm just gonna try and explain what the statement is saying. Né? This part here is a smooth surface. Né? No friction, okay?
Okay.
Then the moment it starts going up the incline, it start on moving on a rough surface. So this will be my rough surface. So this will be rough, ne?
Okay.
So on the horizontal, no friction. So now a rough surface, we're going to have a friction on the up the slope. So now we have the traveling. So the V initial here, it starts with a V initial of 2.5 meters per second. 2.5 meters per second. Okay. Right. So if it starts with 2.5 meters per second, then it rises up a slope of height h, and then before coming to rest. So if it comes to rest, V final, what is V final? 0. You understand what is the statement saying?
No, why is it 0?
No, remember when
coming to rest. Okay. Yes, you're saying that it's gonna come to rest at the end.
Exactly. So when it comes to rest, the final will be 0. You understand?
Yes, I get it.
Okay, let me continue now. So now, remember in an exam, they'll try to give you like a lot of information just to confuse you, or maybe just to see if you can interpret the question, the statement, and answer the question correctly. Now, let's say that we are given the work done by friction. Let's say the work done against friction on the slope, né?
Okay.
So the work done against friction on the slope, let's say we have let's say it's 1.25 joules, né? 1.25 joules. That is the work done by what? That is the work done by friction. So this is my work done by friction. Are you happy with that? You understand what is going on so far, né?
Yes.
And then the question says we need to calculate. Okay. We're going to calculate the vertical height I want to see, Emihle, how you're going to think about this. How can we answer this question? That the box reach on the slope. They want us to find h. How can we go about this?
Okay.
You see now, if you don't give me the answer, I have to give you a serious punishment, because we did talk about this. Remember what happened last time? You still remember what I said on the previous lesson? Remember the height. We talked about something on the height, unless if you want us to go back so that I can remind you what we discussed before we answer this question.
I think I remember.
You remember?
Yes, I think so.
They want us to calculate the vertical height that the box reach on the slope. You see, like when you are a learner and you are in an exam, you see this question and you'll be like, oh, I remember that when we calculate the work done on an object, we consider the horizontal forces, and then now h is not the horizontal forces. How am I going to find the work done by h? Come on, they are playing with me. Remember, if you still remember what we said last time, everything will be good.
So must I explain, you know?
Please.
So, as you can see, height is like, it's like on the incline.
Okay.
So we are able, since we have like theta over there, and then we know that this is a right angle triangle, we're able to use SOHCAHTOA.
You see, now you're going far. You're going far. You're going far, my dear. You're going far. Oh, okay. SOHCAHTOA, yes. I still remember. I'm the one who showed you that. Ne? Okay.
Yes.
Okay.
Yo, I almost cried. So we can use SOHCAHTOA. So we know that if we use sine, we're going to have opposite and a height, right? And as you can see from our theta, that h becomes our opposite.
Yes. So now look at this, né? You see why it is important that you make sure that you don't leave the lesson confused, because whatever that I teach you, né, I know that they will ask this in an exam. Let me explain this again so that you don't forget it, né? So that you don't forget this problem, né?
Okay, sir.
Remember, if something is uninclined, we said that we're going to have the FG, and then we're going to have the FG perpendicular, and then we're going to have the FG parallel, okay?
Yes.
Right. We're going to have the, let me move the FG here. I'm just going to move the FG there. Okay, so this will be my F. Okay, hey, come on, buddy. You can do this. This is my FG, and then we're going to have this as my FG parallel. So now look at this. This is a 90 degrees. Now for now, we're not going to focus on that. And I said that if I have the sine of theta, I can say that the sine of theta is equals to what? It's equals to opposite, which is h, all over hypotenuse, which is delta x, and I'm looking for h. Therefore, what is the h equals to? The h is equals to delta x, the sine of theta. You still remember that part, right?
Yeah, I still do.
Okay. Now, how did we got the sine theta? Because it's opposite all over my hypotenuse, which is delta x.
Yes.
This is my h, okay?
Okay.
Right. So if this is my h, I need to find the work done by gravity from A to B. Look at point A and B. So let's call this point here C. Look at point A to B. I need to find what we call the work done. Let's write this down. The work done by what? The work done by gravity. Gravity from what? A to B. And we said that the work done by gravity from A to B, which formula we're going to use? We said we'll use, this will be the work done by gravity will be equals to the force of gravity multiplied by the displacement. And then remember the force of gravity, this is Fg parallel, because the only one that is parallel is the Fg parallel. Hey, this thing, guys, you just have to, when I emit, you just have to, like, this is Fg parallel. When we say the from A to B, which one is what is this? Which one is horizontal to the surface? Fg parallel. So the work done by the weight on the slope from A to B, the only weight on the slope is Fg parallel. So we need to use Fg parallel. And what is Fg parallel equals to? It's mg, the sine of theta. This will be multiplied by delta x. Do you understand that part? Right. So this is mg, the sine of theta. So now this is the work done by gravity from A to B. But what about if we find the work done by gravity from A to C? What do we get?
From A to C?
Yes.
Are we just going to use Fg?
Okay. Work done by, you see, after I'm done explaining this, then you'll know what to do to answer this question. Eh? You will know what to do to answer this question. So now, we said that the work done by, we're going to say
Isn't it going to be normal FG times that by the distance?
Okay, let me do it. Gravity by from A to C. So what is the work done by gravity from this point here to that point? Can you see that the displacement is, the distance is h now? So to find that, we're going to say,
For h.
Emiche, what are you saying?
I asked you so you can carry on.
Okay, so is the work done by AFG, it's equal to the force times the displacement. But look at this, the difference this time is that the work done this time, it's our FG, which work is parallel to this height. You see this height here, your height h, which force here? Can you see that the force of FG is the one that is parallel? So we're going to use the FG1. You see, this is very important. So this is my FG. The one that is pointing down is the one that we will use. So we're going to use the force of FG because the force should be parallel to the displacement. So when we calculate from A to B, we use FG parallel because it's the one that is parallel to what? To the displacement. But when we calculate the work from A to C, this is my C, we use what? We use FG. So this one instead, it will be FG multiplied by delta X. That is the work done by gravity from A to C. So when it's like this, remember FG. What is FG equals to? FG is just mg times, what is my delta X? It's h. Can you see that my delta, the distance here is given as h, which is the height. Are you happy with that?
Yes. Yes.
And now we know what is height equals to. Look at this. If we call this equation 1, we know that the height is displacement sine x. So it's going to be the displacement sine x. So this tells us that we're going to say my mg, it's what? It's, we said it will be delta x, the sine of theta. So this will be mg sine theta delta x. Look at these two equations. Are these two equations the same? They are the same, ne? So they are the same. Look at this. They are the same, but look at this. The first one is FG parallel. This is the work done by FG parallel. This is the work done by FG. What can we conclude?
That FG parallel is equal to FG.
Okay, what we can conclude, okay, let me just make this thing easy now. What we can conclude is that you look at this partner, therefore we can conclude and say the work done by gravity, the work done by gravity we can always be expressed, by what? Can always be expressed as the change in potential energy. Okay, so now this tells me that the work done by gravity is just mgh. So I'm just trying to explain where is this mgh coming from, because it does not matter if we are talking about the distance from A to B. It does not matter if we move from A to C. If the work done by gravity will be the same. It doesn't matter if we are up the slope, we're moving from A to B, or we are moving from A to C. So what you need to know, since these two equations are equal, we can just say the work done by gravity is equal to potential energy. So now you're going to know how to calculate the vertical height of the box before it reaches the slope. When it reaches the slope. I'm not sure if this makes sense. Are you happy? Can we do calculations?
Yeah.
Come on, Mitch, I did explain this. If you don't understand the concept, if you don't understand everything that we did, you know what I need you to do?
Yes.
The only thing I need you to understand is that it does not matter if this box moves in that direction. Let's say I have, this is my point A, So listen, what we are saying is that the work done by FG, if the box moves from A to B, is the same as the work done by gravity if the box moves from A to C. If it goes down straight or if it moves on the incline. So the work done by FG is just what? mgh. This is what I need you to know.
I get it. It's just that thing that said expressed as the change in potential.
Because this is the formula for potential energy. mgh, is that not EP?
It is.
You still remember that the potential energy is equal to mgh, and it's here on our calc. So this tells us that AP, the work done by gravity, we can express it as what? We can express as the change in potential energy.
Okay, now that makes sense.
You happy with that?
Okay, sure. Yes.
Right. So to answer this question, they said that they want us to find the vertical height. So I'm just going to redraw my diagram. I'll bring my diagram down there so that we don't make any mistakes. So I have a diagram like this. Okay, so this is my diagram. So the diagram moves like this. Okay, so the angle is given as theta and we are looking for h. And the box starts moving from this 10, and the box is 10 kg. So the box will move. Remember we said here, no friction. On the incline there's friction. So it moves all up to up the slope. So this is my box, and we said that the V initial, it was given as V initial, it was given as 2.5 meters per second. I'm just gonna write it that 2.5 meters per second. Then V final, it stops and the V final becomes 0. On the horizontal we don't have friction, so we said that this is a smooth surface. So this one, no friction because it's a smooth surface. And then the inclined part, it's a rough surface, So this will be rough surface. I'm just going to put it here. We're going to say this is rough surface. Okay, let's use this information to answer the question. The question says that we need to calculate the vertical height. Calculate our vertical height. Calculate the vertical height. So if I calculate the vertical height, you're going to see why I was explaining that the weight done by gravity, we can express it as the change in potential. So now we're going to use that. We need to find, we're going to use, remember we are working on work energy theorem. Whatever that we do in this lesson is related on the work energy theorem. So I'm just going to write the work energy theorem down and say the work is equals to times the change in, okay, let's say the work done by the net force is equal to the change in EK. Right, it's equal to the change in EK. So now what we're going to do, we need to identify all the forces that are working on the object, all the forces when it is on incline. So if this is on incline, we know that we're going to have a friction that will go down like this. The friction, it goes down like that. This is my frictional force. Then another force that goes down. What is that other force? Let me not put it on that box. We
Okay.
know that when it is on incline, let's draw a free body diagram. When it's on incline, we're going to have a friction going down. So this will be my frictional force. Then there's another force that is going down, which is the weight. But remember, the weight is the FG parallel, okay? So these are the only forces that are acting on the object. So since these are the only forces, this thing is moving up. So I'm just going to take all the forces that are going up. We don't have any force going up. Then we subtract all the forces that are going down. So this will be the work done by friction minus the work done by what? By Fg, by the weight. We're going to equate this. So let's quickly change this so we can write it properly now. We take up as positive. So we're going to say the work done, if I say my work done is equals to the change in EK, this will be all the forces going up. We don't have any forces. We minus the work done by what? By frictional force. We're going to minus the work done by the weight. We equate this to 1 over 2 m mass inside the bracket will have Vf squared minus V initial squared. You understand?
Yes, sir.
Okay. So now, when it's like this, we just have to understand. Remember the work done by frictional force was given. They said the work done by frictional force is 1.25 joules, but it's going to be negative since it's going down. So I'm just going to subtract that 1.25 there minus the weight. For now, the weight, I'm just going to substitute that weight. Maybe before we do the substitution, let's just change some of the things here. Né? Let's just say this will be, okay, let's say this is going to be minus the work done by friction minus, so we said that the weight is going to be what? It can be expressed, the work done by the weight, it can be expressed as the change in potential. So I was trying to make you understand why the work done by gravity can be written as mgh. So all this was to make you understand why is the work done by gravity equals to mgh, okay?
Okay.
Right. So now I'm just going to substitute this as mgh. We're going to say this is equals to 1 over 2 m into Vf squared minus V initial squared. Remember, the weight, we can express it as mgh. So let's do the substitution. This is minus the work done by frictional force was given as 1.25 joules minus the mass of this is just 10 into 9.8, and we are looking for h. This is equals to 1 over 2, the mass is 10, inside the bracket V initial is 0 minus initial of 2.5, that needs to be squared. So negative 2.5 squared. Please don't make a mistake and say this is the minus it's inside the bracket. No. So when you work this thing out, you'll be able to find the height. You just have to work it out step by step, okay?
Okay, sir.
Right. You can try work this thing step by step and find the height. Guys, what did we miss? Someone is saying, what happened to sign? Which sign? He forgot to edit, but that it is there. When I learned now, so you forgot to include sign date. I'll try to go back up and check what we forgot to include. Oh, the sign date on the equation, né? The sign date, né? I'll definitely check it, né? I'll definitely check it, guys. I can see your comments. I will definitely check it. We still have 1 hour to push. Because now, if you understand the work energy theorem, we're going to move to what we call power. Then once you are done with power, you are ready for exam questions. Ne? Emishi.
Yes, sir. I got 0.31.
You got your answer as 0.31. That's your height.
Yes.
Very good. So now if you substitute correctly, there's nothing to worry about. Ne? So the height, if we isolate this, I'm just gonna let me show the steps that we can go through to isolate this. I can just leave, maybe I can just say this is minus 1.25, ne? And then let's bring the half of 10. I know that half of 10 is 5. Let's bring the 5 this side to be negative 5, and inside the bracket we still have negative 2.5. This is squared. You see, I'm just paying attention, and I'm gonna move the 10 into 9.8 the other side, and this is what? This is h. So the everything that you get, you need to divide by 10 into 9.8. You need to divide everything here by what? By that 10 into 9.8. This way, I think we're even going to avoid rounding off. We can only round off the final answer. So my h is equal to 0.31 meters. So this is my h. Are you happy with that?
Yes, sir.
And now congratulations, you understand work, energy and power. Ne? Let's start with a new topic.
Okay.
But we are still working on momentum and impulse, work, energy and momentum, whatever they call it. But now we're going to start with power. Okay?
Okay.
Right. So we're going to finish this thing today. Then from tomorrow we'll work on past papers. Let me teach you how to see the tricks and how to attack them. Ne?
Okay.
Then Thursday and Friday we can do maths.
Okay.
Then this tells me that we've covered 8 hours this week.
Yeah.
Nice. Okay, so on power, what is power according to your own understanding? What is power?
Your power.
Yes.
It's like I don't know.
So power is the rate at which energy is transferred. Someone can say is the rate at which work is done, or we can say is the rate at which work is done, or you can say is the rate at which energy is transferred. Ne?
Okay.
And the formula that we'll use to calculate power formula is equals to W over delta T, where P stands for power and it is measured in watts. Ne?
Yes.
Okay, so P is power. So my P, this P will be power and it's measured in watts. The W will denote the work done. So the W is the work and it's measured in joules, and we have this as the time. So the time is always in seconds. Ne? So now listen, if the object is traveling at a constant velocity, right? I know that most of these things you miss it at school when they teach it, or you miss it when you practice. Ne? So I need you to know that if I have what we call if I have an object that is the object is traveling at a constant, they'll give you these things in a statement. They'll just say, please note that the acceleration of this is constant. Ne? Constant velocity. What I need you to understand is that if the object is traveling at a constant velocity, we're going to say the average power required to keep it at a constant velocity. Will be equals to FV. So now when you see that you are working with power questions and you hear the statement saying that, constant velocity, just know that the power required to keep that object in constant velocity will be FV, where F is your what? F will be the force, will be the force, and then we're going to say our F is the force. Let me quickly note this down. This will be my force. Oh, F is power. This is your power, and we said power is measured in watts. This F is your force that is measured in newtons. So V will be the velocity. So V will be your velocity, okay? Your velocity in meters per second. So now, power is a scalar quantity. So we don't have direction for power, ne?
Okay.
You understand?
Yes.
Okay. So now, we're just going to work on a problem. Let's say that we have, let's say, this is an example, ne? This is good, especially for IEB student. It takes, let's say it takes a motor. Can you drive?
Yeah, kind of.
Kind of, ne?
Yeah, I'm still learning.
Okay.
Can you drive, sir?
Yeah, boo. How?
To what? To what, sir? It takes 2 minutes to?
It takes 2 minutes to lift. Thank you, ne? To lift 2000 kg, and then we say, let's say through a height of 10 meters, ne? So now, from rest, look at the question, ne? From rest. So, at height of 10, let's say they tell us that at height of 10, at height of 10, they say at height of 10 meter, the cartoon is traveling at 1.5 meters per second. Ne?
Mm-hmm.
Let's determine number one, the work done by the motor in lifting the cartoon. So we need to find the work done by motor in lifting the cartoon 10 meters. Ne? So which formula are we going to use to find the work done by the motor?
Which formula are we going to use?
Yes.
All the motor. Yeah, the height.
Remember the work energy theorem?
Formula.
Yes.
Yeah.
That's what we're going to use, ne?
Yeah.
So they said that it takes 2 minutes to lift a cartoon of mass 200 kg. So what I'm going to do, I need to identify all the forces that are acting on the object, ne?
Okay.
Right. So if we find this one, we need to find the work done by that motor, and we need to find the work done by the gravitational force. So we are lifting something up. We take something up. So if we lift, there will be work done by what? By the motor. So we're going to call this Wm, and there will be work acting down, which is the work done by gravity. So if we take up as positive, this side we're going to say that we have the work done by the motor, then we're going to subtract the work done by gravity, and then we're going to equate these to 1 over 2 m inside the bracket. I'll have the Vf squared minus the V initial squared. So now we said that we can express the work done by gravity as what? mgh. It's equals to 1 over 2m. Then I have Vf squared minus V initial squared. Now we can do the substitution. So now minus the mass of this is 2000, and then this will be 9.8. We need to multiply this by the height. That was given as 10 meters. So the height is 10 meters. So I'm just going to substitute the height of 10, then equate this to 1 over 2, the mass of 2000 rands. We like money, though. And then V final squared is given as 1.5. If we can go back and see, they said the cartoon at the height of 10 meter, the cartoon is traveling 1.5, but remember it's from rest. So V initial is 0, and this is your V final. Are you happy with that?
Yeah.
Okay. So now what I'm going to do, I can just substitute and say my V final squared. I know that the V final squared will be 1.5, and this should be squared. We're going to minus initial of 0. We just have to find m. We just have to isolate this and find m. So the work done by the motor will be 1 over 2 into 2000 rand into 1.5, that is squared. Close the bracket. We're going to bring that guy to the other side to be positive. So this will be 2000, 9.8 into 10. So when you do this, what is your answer? What do you get? What is the work done by the motor? What is this equals to?
I get 21,850.
Okay. You get what?
21,850.
Did you punch this correctly? We forgot.
I punched.
Hmm?
I punched it just like you punched it, so. Must I redo it?
Yes, please. Because okay, this should be same as half of 2000, it's 1000 rand. We need to take the 1000 rand, multiply it by 1.5, that is squared. Then we add 2000. The issue is that I don't have a calculator on my side.
No, I get 198,250.
Okay, nice. So the work done is equals to 1982. Thank you. 1982.
Yes.
50 joules. That is the work done by the motor for lifting the object, ne?
Okay.
Right. So now, most of the time, they'll ask you to find the power output. Trust me, ne? You might get this type of a question, or you'll get it on a multiple choice. They'll say, calculate the power output. So the power output is not the same as this equation, because if you use this equation, things will start going, but it's fine. Let's use this equation. But when we use the equation, let's say the power output we said is going to be the work done over time. Ne? So the power output, we're going to say P is equals to W over T. Now we just have to substitute the work done, the one that you just calculated, 19,8250, divide by the time. They said this will take what? 2 minutes. Remember, time is measured in seconds. Ne? So 2 minutes should be converted in seconds. This is where most of the learners forget to convert and they're going to lose marks. So T is equal to 2 times 60. Therefore, this is 120. Therefore, the answer that you get is your power. What is the answer? What do you get when you divide these two?
I get 1652,08.
We said this is measured in what? Are you happy with calculating the power output?
Yeah, what is the power output, sir?
The power output is like saying they want you to calculate the power. Remember, it takes a motor 2 minutes to lift the car. And we said that power is the rate at which energy is transferred. So now we are transferring what? Energy. So when the motor is lifting, the motor is doing some energy. So now we need to find the power output. You understand? It's like they just want you to find the power.
Okay.
Okay, now let's answer this one. Let's calculate the percentage we need to find the percentage of the motor if it is rated 220 volts and the current is given as 10 amperes. Ne?
Mm-hmm.
Right. The percentage efficiency we talk about when you see this thing, just know that this refers to, remember that, or let me explain this before we can do the calculations. Ne? This thing, remember we are talking about a motor that is doing work. Ne? So when a motor does work, just know that all the input power is not always transferred to the output. So when a motor does work, we say that all the input is not always transferred to the output. So now the formula that you can use to calculate the percentage efficiency, so we're going to say the percentage, we're going to use the formula that says power output, which is the one that we just calculated now. We need to divide this by the power input. The answer that you get, you multiply by 100%. Please don't say 100, ne? 100%. On your calculator, you should write also the percentage. We're not multiplying by 100, okay?
Okay.
Right. So the power output is the one that we calculated on the previous question. It's equal to 1652.08. I'm just going to substitute that on top. So this will be my 1652.08. You understand where is that coming from, right?
Yes.
What about the power input? I need you to go to your formula sheet, ne? Okay, can we quickly get past paper first so I can show you how to find this, ne? Let's do physics past paper. I need a formula sheet first so I can just quickly show you how to do this. We need a formula sheet for paper 2, P2.
Okay.
Just gonna look for the I want to train you, ne? Look at this. If we go back to the statement, ne? Wait, why am I saying paper 2? This is paper 1.
Yeah, I was lost.
But you don't correct me, ne? Why?
The thing, I'm like, sir, maybe like you have a formula in paper 2.
Ah, come on.
You never know, yo. Okay, I'm in paper 1 now.
Yes.
The formula.
Yeah, let me also, remember I need to show you this so you can understand what you need to do. Because you see one thing I like about physics question, even if you don't know what to do, you can still get your answers correct. For example, they say calculate the percentage efficiency. So you know what you're going to do. If you know the formula, you know how to calculate the power in, the power output. But how about the power input? The power input has to do with what you are given on the statement. Look at the statement. They say that it is rated at what? The motor is rated at 220 V. And so now this is the voltage, this is the what? This is the current. So we're going to look for the formula sheet that has to do with power, current, and voltage. Let's go and see if we can find that formula. You see, that's how easy it is. You just have to check what you are given. Eh?
Okay.
Let me quickly, I know that we might not even get the formula sheet here. You see, these people who edit these past papers, straight. How?
I will.
How do you, they don't put like Bahai or something.
You are sad.
See, now I'm on paper 2. Serious, it's like they are high or something. I'll just go straight to Department of Basic Education. I'll just go and get the past paper from our enemies.
You and they are our enemies.
I'm just gonna go there and get paper 2. How? Why paper 2?
So I think you miss paper 2 now.
Yeah, in fact, paper 2 is my favorite. Even maths, my favorite is paper 2. Even physics, my favorite is paper 2. Okay, let's look at this question. I need us to check formula sheet. Where's the form? Oh, this is the formula sheet now, and we're working on work energy. Look at this now. Let's hope we'll find what we are looking for. If we don't get it, don't worry, I'll explain that. Can you see my formula sheet?
Yes, I can see it.
Okay, I don't think what we are looking for is here. P is equal to W over delta, and we are looking for P right, because what I'm looking for, let's go to seconds. Where's the formula for seconds? There we go. We're born. Can you see? Now I'll never like there's no way I don't. If you give me a past paper, shame. Or if you give me an exam, there's no way I'm going to fail. Look at this. I'm given the voltage and the current, so I know which formula I need to use. So this tells me that the power input will be what? Why you fail when you have the formula sheet? You know that it will be what? V times I. So it will be 220. We need to multiply with the current, which is 10. You see? So now what I'm going to do, I'm going to use that formula to find my power input on what we are given. So the power output, we calculated it, and then now, because we know that the power output, it takes us 2 minutes to do that, and the work was 19,8250. So now we have the power output. We need to find the power input using the given information. So this will be 220. We need to multiply this by the current of 10. The answer that we get, we multiply this by 100%. You see how easy this thing is. So now I don't have to explain where is the 220 times 10 coming from, because you understand that P can be expressed as V times I. You just have to go in the formula sheet to check. Do I have the formula that I can use, because we are looking for what? For power. Do I have any formula that I can use that has V and R? Yes, and it's there on the formula sheet. Are you happy with that?
Yes, sir.
Now tell me, what is the percentage efficiency if you put it on your calculator? What is this equals to? What is your final answer?
0.75.
0.75. You see, you're making another mistake. I said not by 100. 100%. You need to write percent on your calculator, because you might forget to multiply that answer by 100 again.
Yes, sir. I get 0.5. I put the percent in.
You got 0.5?
Yeah. 0.75. That's what I got.
0.75.
Yeah. If I say...
The answer should be big. It should be big, like 50%, 75%. So if it's 0.75, if you convert it, it should be 75%. You understand?
Because if I'm going to say with the 100%, I'm getting 0.75.
Okay, remove the percentage. Tell me what you get, because we need to fix this now.
It's 75.09.
Okay, then I guess we'll have to remove the percentage, né?
Okay, so the percentage mustn't be on the calculator.
Yeah, but when you write the formula, try to write it. Let's not remove it on the formula just to be on the safe side, né?
Okay.
You get it?
Okay, maybe it's the setting of this calculator that I'm using.
Nah, it's fine. I understand why you're getting this, but let's remove it like this. Then we're going to say this is 7.0. You said 7.09%. Are you happy with that?
Yeah.
Okay.
Yeah.
Right. Let's go back to incline, né?
Mm-hmm.
Let's put the object on incline, because now you're about to learn something new again. So on inclined, we're going to say this is my theta, and then we're going to have the mass that is on inclined with 225 kg. Then let's say that this mass has the velocity of what? The velocity of 72 kg kilometer per hour, ne? Okay, so now a motorcycle travels up a rough incline. So this thing, it travels up. Okay, then the incline at a constant up at, you see, I'll give you at a constant velocity. You said, remember we said that in a statement they'll say constant velocity. When they say constant velocity, what should come in your mind when we calculate the work done by the, we said, let's go back up.
Also 0. That's when it's at rest. Sorry.
Where did we talk about the... How? Oh, there it is. If the object is traveling at a constant velocity, power is F times V, ne? Don't forget that, ne?
It's F times V.
Yeah, so if they give you a statement and say that it travels up at a constant velocity of 72, the constant velocity 72 kilometer per hour, and then they say that at a speed, at this speed, we are given the output power. We are given the output power. And they said the output power is equals to the output power of the engine. It's 125 kilowatt. You understand what we are doing here? We have a motorcycle that is traveling up a rough inclined slope. So at a constant velocity of 70, and the constant velocity is 72 kilometer per hour. At this speed, the output power of the engine is 125 kilowatt. Ne?
Okay.
We need to answer the following question. Number 1, let's determine the motorcycle velocity in meters per second. They want us to find a velocity of that object in meters per second. Do you know how to convert from kilometer per hour to meters per second? Do you know how we convert?
No, I don't, honestly.
You don't know how we convert? Please don't forget this. Ne? When we convert this, we just take the given velocity, you divide that by 3.6. Ne?
3.6.
Yes. You want me to explain where the 3.6 is coming from? Come on. Trust me, it's 3.6. Like, if I say I have 72 kilometer per hour, I can write that per hour as times 1 over age. You understand?
Mm-hmm.
And then now I need to do what? I need to say, if you can check 1 hour, in 1 hour we have how many minutes? 60 minutes. Then if it's 60 minutes, we also have seconds. In 1 minute we have 60 seconds. I'm not sure the best way to explain this, but trust me, we just have to take this divided by 3.6.
Okay.
I'll just find the best thing to explain this, then I can send you a picture so that you can see how the conversions works. Because if I have meters per second, inside seconds I have in 1 minute, I have, what is this? In 1 minute I have 60 seconds. Ne? So this will be 72 point, or it's just 72. We're going to take the 72, you divide that by 3.6. So we always divide by 3.6. And if you move from meters per second, you want to go to kilometers per second, you can multiply by 3.6. Ne?
Okay.
What is the answer that you get?
20
meters per second. Then the second question says that we need to determine the force applied by the motor.
Mm-hmm.
You don't have to stress. You just have to think, oh, I'm given the power. I have the output power. I have the velocity. Which formula will be best? This moves at a constant velocity. So power is equal to the force multiplied by the the velocity. So what is the power? It's given as 125 times F, and the velocity, we calculated that to be 20. You understand? You just have to do what? The power, we still have to convert the power. Remember, the power is in kilowatt. We need to convert this into watt, and we're going to multiply that by 10 to the power 3. Most of the time I just say 10 to the power 3 instead of saying 1000. I just say we multiply by 10 to the power 3. So my power, it should be in watts. Né? We need to convert that. They almost got me. That was a trap. I didn't see the kilowatt. So now this is going to be 125 times 10 to the power 3. You understand the conversions?
Yes, sir.
Okay, so now from this, what we're going to do, we need to make F subject of the formula. Therefore, my F will be 125 multiplied by 10 to the power 3. Divide this by 20. The answer that you get is your force, and it should be in newtons.
It's 6,250 newtons.
6,250 newtons.
Yes.
Let's answer the last question. Let's say that the motorcycle has a mass. So we can see that the motorcycle, the mass is 225 kg, and the length of the slope is 20 meters. So let's say now we are given the length here. The length of the slope, let's say this is delta x, it's equal to 20 meters. Né?
Okay.
So I'm just going to bring my object down here so I can work on it properly. This is my object. I have this as theta, and this object has the mass of 225, and we know that the velocity is 20 meters per second. Né?
Mm-hmm.
And then the distance of the slope, I'm not sure how I'm gonna do this, but you'll understand that the distance is 20 meters. Né?
Yes.
Now we need to say if we are given that the force of friction, if the force of friction, let's say the force of friction is given as 5,150 newtons, let's calculate the angle of inclination.
Oh.
The angle of incline. So let's say this is the information that I have, and I want to find the angle of incline. I don't want you to stress. Né? Remember, I said each and every time you see the weight angle of incline, what should come in your mind is my FG perpendicular, which is mg, the cos of theta, and I'm going to say FG parallel is equals to mg, the sine of theta. So the theta is that angle of incline. Whatever that you do on your formulas, on whatever that you do, you need to have FG parallel or FG perpendicular. So I'm just gonna use, because it's easy for us to find the work done by forces on that box that are parallel to this displacement. So what I'm going to do, first thing, I'm gonna write my free body diagram indicating all the forces that are acting there. Remember, we said this thing go back up, there is travel output, what the force applied by the motor. So this is going up, and the motor is going, it's applying a force, an upward force. So this is F applied, it will move up, then the FG parallel always go down, and then we're going to have the frictional force going down. So this will be my F frictional force. Do you understand my the forces that
Yes,
are
sir.
acting on that diagram?
Evil.
You good?
Yeah.
100%. So now look at this. I can choose up as positive. If I choose up as positive, I can find, say, my F net is equals to ma, but remember they said constant velocity. Constant velocity means that my acceleration is 0, so I can equate this to 0. You see, whatever that you learned in Newton's law, you can apply it here. So the constant velocity, I'm just going to say my F net will be equals to 0. So I can say F net is equals to 0. Then I can say my F applied minus all the forces that are going down. We minus the frictional force which was given, equate this to 0. The applied force, if you got this applied force wrong, this will affect everything. So I'm going to put this as 6,250 minus FG parallel, it's mg, the sine of theta. So I can say this is, before we do the substitution, let's change that FG parallel. So this will be my F applied minus mg, the sine of theta, minus f, it's equal to 0. Then we can do, say, this is 6,250. We minus the mass was given as 225 into 9.8. The sine of theta, because we are looking for that theta, we need to minus the frictional force that was given as 5150. So this will be my 5150, equate this to 0. What's next? We need to solve for sine theta. So I'm going to say 6,250. I need to minus 5150 and equate this to 225 into 9.8, the sine of theta. So whatever that we get that side, we need to divide both sides by 225 multiplied by 9.8. The answer that we get here, we divide everything by that 225 into 9.8. So now what is the sine of theta equals to?
It is equal to 0.5. I got sine of theta, I got 0.45.
Okay, if you round it off, it's 0.5, ne?
Yes.
Now, what is theta? Remember we use the sine inverse, great terms work. What is sine inverse of 0.5?
Okay, sine inverse of 0.5. 30.
Okay, theta is equal to 30. So, Emilia, tell me, do you have any questions based on what we've covered so far?
No, sir.
You're good?
I just need to study it because it's a lot of formulas. Yeah.
Okay, but let me tell you now. What I can say is that congratulations, you now understand work energy theorem. You can start with past papers, but before you do that, just make sure that you understand everything that we've covered today. Ne?
Okay, sir.
Yeah.
And then do past paper.
Yeah. Before you do past paper, make sure that you are happy with everything that we've discussed on this session. Ne?
Okay, sir.
All right. I'm not sure if now I don't think it will be best for us to do a past paper. Ne? I don't think it will be best for us now to do a past paper, but let's just do easy stuff because we still have the 15 minutes. I don't want to owe you any more hours now. Ne?
Okay.
Unless if you want to donate the minutes and say, sir, it's fine, you can end the lesson and prepare to go to work. The 15 minutes is on me, then I can definitely do that. Trust me.
No problem, sir. You can go.
Are you sure?
Yes, because I wanna first study this whole thing
before we do a past paper.
Yes.
Okay, no problem.
Yeah, so it's okay, sir. You can go. You don't owe me minutes.
Okay, thank you very much. I guess Christmas came early today for me, ne?
You did a good job. You pushed today.
Yes, and we're done with energy. The work energy theorem. We're done with everything on that part. So once we do past papers, we're going to start with. I think we can now maybe jump to paper 2 and start with chemical equilibrium.
Okay.
Yeah, we can start because if we can do chemical equilibrium, but I think it's best if we start with something that can motivate you. You can choose between acids and base and chemical equilibrium, which one you want to do first. Ne?
Okay.
Yeah. Thank you very
Okay.
much for attending. I'll see you on our next lesson tomorrow, ne?
Okay, sir. Tomorrow.
Yes, morning. Remember I said we'll work until Friday this week.
Okay, so tomorrow, Thursday, and Friday.
Yes.
Stop. No problem.
Sharp, sharp. The YouTube part, do you guys have any questions based on what we worked on today? Are you all happy? I'm just gonna wait and see if we have any questions from YouTube. Are you all good? Okay. I guess no questions. But if there's something that you don't understand, please make sure that you go through the lesson again. You watch the lesson, you pause, you work, and make sure that you understand everything. Now, thank you guys for joining the lesson. I'll see you guys during the day for our next lesson. We'll just discuss which topic we're going to push during the day. Now, remember the time from 12 to 2. Thank you, Onalinda. I'm happy that you are still in the lesson. Now, I'll see you guys during the day. Maybe now you can just take a break or work on something, watch other YouTube videos for alternative methods on how to work on energy theorem. Thank you very much. And this is where we're going to end for this morning. Sharp, sharp. Yes. I'll definitely share yesterday's lesson. I will share the yesterday's lesson. Don't worry.